Hey everyone, welcome to another video in which we'll go through chemistry passage questions. First, I'll zoom into the passage here so that you guys can go through the passage and then attempt the questions on your own by pausing the video, and then you can look at the answers as we go through them together. So here's the passage. More of the passage. And now the questions. Okay, there are a few more questions over here. And that should be it for the questions. Okay, so hopefully you guys attempted all the questions on your own, and now we'll go through what the correct answers are, how to interpret the passage, and how to find the key information that each question is looking for. So in this passage, 5 students, they use volumetric analysis to determine the molar mass of a weak acid of unknown composition. Table 1 lists the acids issued by the instructor as unknowns. So in this case, this is a very typical undergrad chemistry lab experiment. You have an unknown acid, but you do know that it's a weak acid, okay? It's not a strong acid, and you're using volumetric analysis. So essentially what you're doing is a titration. You don't know what your acid is, but you know that it is an acid, and then you start titrating or adding in a bits of a base, and for the base you do know what its concentration is. If you know the concentration, and then you also know the volume that you're adding based on how many drops you added, then you can figure out the moles of the base that you added, and then that should translate into the moles and then the molar mass of whatever acid you have. So these are the potential weak acids that the students could have, and then by looking at this, well, I guess they'll know the molar mass, and then the only thing that's missing is moles, which you'll get from the titration, and then that should give them the identity. And just quickly here, notice here, table 1, it says they're weak acids, and then the first one is an acetic acid, which just looks like this. And then based on the names and these chemical formulas, you should know that all of these are carboxylic acids. And carboxylic acids, like acetic acid, those are like one of the go-to examples of weak acids, and we talk about them when we're talking about buffer systems. So you should know that these are all weak acids. Going along the passage, it says the instructor prepared a solution of sodium hydroxide by dissolving 8 grams of sodium hydroxide. So first they took the solid form, and then they dissolved it in 2 liters of water. We're given the molar mass, we're given that it's 2 liters of water, and then it's as shown in equation 1. The temperature of the solution rose during the mixing process. Okay, so this is equation 1, just mixing the solid form, the powder of sodium hydroxide with water to turn it into the aqueous form. Now you've got your base that you're doing your titration with, and then this base was standardized by each student by titration against a pure sample of KHP, which is just potassium acid phthalate, and the molar mass of that was given to the students as shown in equation 2. So you look at equation 2, you're reacting this thing KHP with sodium hydroxide. And the key thing here is that you know that this is a pure amount of KHP, and you know what its molar mass is. So because you know what its molar mass is, then you'll be able to know exactly, based on how much volume of the compound you're using, then you'll know how many moles there are. So you know exactly how much of KHP you're using, and you know according to this reaction that it should be a 1-to-1 ratio. So even if there were some errors, like human errors that were made with the sodium hydroxide where its concentration isn't exactly what was intended, like the instructor tried to make as close to the intended concentration as possible, but there's always some errors, like maybe you might drop a little bit of your powder or whatever that happens. So they just want to make sure that everyone standardizes it so they know exactly what the concentration of their sodium hydroxide is, and then their calculations won't be wrong due to any human error. So That's what the whole point of the standardization is. So next, each unknown was dissolved in approximately 30 milliliters of water, or water ethanol, and then it was titrated with the standardized sodium hydroxide, as shown for benzoic acid in equation 3. So this is an example of what would happen if an acid reacted with the sodium hydroxide, and then of course you get your neutralization. You get the formation of the salt, which is just the deprotonated form of the acid plus the sodium ion, and you get water. And then finally, they gave us a second table, which is the partial data of students A to E. So in the top over here, you see the identity of the student. Over here on the left side, you see that they're writing down the mass of the KHP that they measured. Therefore, they found out the moles of KHP, and then all of these other volumes and moles and all the data that they found out from doing their experiments. We don't have to go into the details. It's likely that the questions will refer us back to that table, so we'll go to it when we need to. Now, getting into the questions. The first one is asking us how many moles of KHP are present in the sample of KHP of student A. So we want moles. That's what we're looking for KHP, and then we're looking at student A. So that is something that we must get from this table right here. Student A, they told us 0.55 grams of KHP, and we're looking for moles. So quickly, moles is mass over molar mass, so we know it's 0.55 grams, and then the molar mass for KHP was given in the discussion of KHP. Here's KHP, here's its molar mass, 204.2. 204.2. So this question is really just find the data that you need from the passage and then do the calculations. So I'll do these very roughly, doing it in a method that I would do it if I had pen and paper. So this might kind of go on for a little while. If you can do it faster, then just kind of skip ahead a little bit. You can use a calculator as well to get the actual answer, but I'll go through how I approach math problems, and sometimes it's a bit long-winded, but I eventually do get to the answer. So just feel free to do this on your own, however works for you, but know that this is a mass, that's a molar mass, and so this is 204.2. That's the molar mass, and you have to just find out what that answer is. So I can turn the 0.55 to just 0.5 at the top, and the 204.2, I can turn that into 200 grams per mole. And then for me, it would be easier, because I don't want to deal with decimals, I don't like dealing with them, if I just multiplied both the top and the bottom by 10. So that becomes 5 over 2,000. I'll leave out the units for now. Okay, 5 over 2,000. 5, it goes into 100 20 times. 5 goes into 1,000 200 times, and so 2,000 is just 400 times. So then that equals 1, because I'm dividing both by 5, right? And dividing by 5, top to bottom. That gives me 5 over 400. Okay, now if I look at all the answer options, these are all in decimals. So now it's just, can you turn this fraction into a decimal? The 1 over 400, that's the same thing as like 1 over 4 times 1 over 100. Okay, those numbers are much easier to deal with. 1 over 4, I know that that's 0.25. It's a quarter. And then this 0.01, that's 1%. Now if I were to multiply something with 0.01, this is much easier to deal with. If it's like 0.0001 or like something with like a 1, you know that you just have to move the decimal places around. Like this guy, this is pretty much the same thing as 10 to the negative 2, which just means move the decimal place 2 places to the right. So this, which means that I'm working now with 0.0025. Sorry, accidentally zoomed out. 0.0025 moles. But everything in the answers is 2 point something. So if I want it to be 2 point something, now I just have to move my decimal point back. So I moved it forward 3 times. That means that this is equal to 2.5 times 10 to the negative 3 because I moved it 3 forward. So really it should be 3 places backwards. That's where the decimal should be. Moles. That is now my final answer, okay? 2.5 times 10 to the negative 3 moles. Now, whenever you do a simplification or a rounding, you should know that that's going to affect your numbers. In this case, since I reduce the numbers that I'm working with, I can kind of estimate that the real number is going to be slightly higher than this. In this case, what's most important is the exponent, the 10 to the whatever, and my answer was 10 to the negative 3, so I'm going to go with the one that was also 10 to the negative 3, which is C. And if you were to use a calculator and do the actual calculation, 0.55 divided by 204.2, this is the number that you would get, the one that you see in C. So just keep that in mind. In this case, it was easy because we could just look at the right exponent, but a lot of times you'll get all the answer options, like they might all be 10 to the negative 3. So then you really have to figure out which one was the correct one. If you can use the actual numbers, do it that way. But if you round, know that like in this case, since I reduce the numbers, it's going to be a slightly higher number. In some other cases, like if I don't affect the numerator but I affect the denominator, then that will determine if the number is lower or higher. Just keep all of that in mind when you do rounding, because with rounding it's very easy to accidentally choose the incorrect answer. But in this case, the answer options, they're pretty helpful and they don't try to trick us or make it super hard by having different exponents, so it was easy to find out the correct one. Now that one aside, let's move on. Which of the following changes in state functions occurred during the dissolution shown in equation 1? So look at equation 1 and then tell me about the state functions, meaning enthalpy, entropy, and if it's spontaneous or not. So equation 1 is just if I have the solid form of NaOH, now it's going into the aqueous form. So NaOH, you can kind of think of that almost like you would NaCl, right? It's something that's connected before, but then NaOH, what it actually exists as in the aqueous form is Na plus OH minus, so it breaks up into ions, whereas before the ions were together. And whenever you have ions and they're packed together, they're in a very ordered state, so kind of like a crystal lattice, whereas when they split up, the ions are free and they're running around in solution. So if you had one thing and now you split it up into 2 things, more things means that there are more microstates that those objects can adopt, therefore it's higher entropy. So entropy definitely did go up. Let's see. Yeah, this one is correct. We're told here the temperature of the solution rose during the mixing process. So if you're carrying out some reaction and then you're seeing that the solution temperature is increasing, that means that that molecule is releasing energy to the surroundings. So it's releasing the heat. That means that enthalpy must be negative, which this one says it is, right? Makes sense. There was energy in the bonds that were holding Na and OH together, and then in this case, it always depends on the specific reaction, but in this case, breaking out those bonds released some energy. Whenever you have a process where enthalpy is negative and energy is released, that's more likely to be favored and it's going to go forward and it's going to be spontaneous. So in this case, that is a good thing. Otherwise, if the solution got colder, that means that energy was needed to help the molecules in the reactant side get over the energy barrier, and enthalpy would therefore be positive. And in this case, the person put the NaOH in water and it dissolved spontaneously. The reaction went forward. We're not told that they had to do anything special to make it go forward. You just dissolve it, maybe like mix it a little bit. So it does seem like a spontaneous reaction, especially when you have a negative delta H and you have a positive delta S or entropy. At any temperature, this is going to be a spontaneous reaction. It might be a different case if one or both of these were in an undesirable state, but in this case they're both desirable, so definitely spontaneous reaction. Which of the following state changes occurred? Wait, let me just double check that. Oh, sorry, I misread that. It's a spontaneous reaction, which is true. So 1 and 3 were correct, but for a spontaneous reaction, delta G should be less than 0. Delta G should be negative for a spontaneous reaction. Okay, and in this case, option 2 is saying delta G is positive, implying that it's non-spontaneous, and that's incorrect. The reaction is spontaneous. So therefore only 1 and 3 are correct. Moving on to the next question. What is the approximate molarity of the solution prepared by the instructor? So there's a solution prepared by the instructor, that was the NaOH. We're asked for its molarity, okay? Molarity, moles over liters. This is where the instructor did their thing. And I can see that they used 8 grams. Here's the molar mass, and they did it in 2 liters of water. 8 grams over 40 in 2 liters. So the moles were 8 grams over 40 grams per mole. And that is just equal to, if I divide both top and bottom by 8, 1 over 5 moles, which is equal to 0.2 moles. That's how many moles I have, and then the concentration, that's moles over liters. So I had 0.2 moles over 2 liters. So pretty much just divide that by 2. So 0.1 molar. So that is my final answer. That matches up with option A. So another calculation question. Hopefully it wasn't too difficult to find the information that you need, because they talked about the solution prepared by the instructor. So make sure you find NaOH and not the solution solution or the reaction that the students performed, which was the thing with KHP. So as long as you understood all of that, in this case the calculation was much simpler than the one in the first question. So moving on now to this question, 32. At the stoichiometric or the equivalence point in a titration of benzoic acid with NaOH shown by equation 3, the pH is what? I don't even really need to go to equation 3. All I know is that I'm at an equivalence point. Benzoic acid is now at equivalence with NaOH. So at the equivalence point, that's when I have, equal moles of the acid and the base. At this point, what happens is dependent on the nature of the acid and the base. We're talking about benzoic acid here, and repeatedly in the passage, we're told that we're looking at weak acids, okay? Weak acid, weak acid. I probably mentioned it later on as well. So we're looking at weak acids. NaOH, you should know, like that one should just be obvious that it is one of the most well discussed examples of a strong base. When you have a strong acid and a strong base and they reach their equivalence point, the pH will be 7. Because when something is actually a strong acid, that means that it's going to dissociate into very close to 100% of the conjugate base plus the proton. So it's going to release the proton. Whereas a weak acid won't release all of its proton. Maybe most, or less than most, maybe a bit less than half. But it really depends on how weak the acid is. The point is though, it's not going to release all of its protons, meaning that if you have 100 in a solution, right? If you have 100 molecules or whatever, or 100 moles, let's say, then maybe more than half will release their proton, but it won't be 100% dissociation of the entire population, you could say. So because of that, on the other hand, when you have the base, and in this case it's a strong base, right? NaOH is fully going to dissociate into Na positive and then OH negative. Because of that, there's a lot more of the negative thing. There isn't that much of the positive thing. If they're released in equal amounts, then they cancel each other, and then the pH is 7, which is neutral. So you can kind of think of this as like a tug of war. If they're both strong, then it's a draw, and the pH is at the midpoint. But if one of them is weaker than the other, then the pH goes towards whichever is stronger, the nature of that. So in the case of an acid, if an acid were stronger and the base was a weak one, acidic pH is low, so therefore the number would be less than 7, the pH. If I have, in this case, a weak acid and now a strong base, the pH is going to be greater than 7. So it's going to be a basic pH. In this tug of war, the base is going to win. So that matches with option D. And right now I'm not going to go into the details of like why this happens, but you can look that up if you are really interested, if you really want to know why the pH goes to one side or the other. But really the key thing that you need to answer this question is just knowing whether it's above 7 or below 7. Next question, what is the conjugate base of chlorobenzoic acid? So chlorobenzoic acid, tell me what its conjugate base is. And we're just given the chemical formulas of the things over here. So I'm looking at chlorobenzoic acid, and that would mean that I have to refer to table 1, which shows me the chemical formulas of all the different acids. So if you just look at it, like look at acetic acid. Here's the chemical formula. I've given you over here the structure for it. So you can see that there's an H first in the chemical formula, and then C2H3O2. So it's very obvious where the two oxygens are. Those oxygens are telling me that I have a carboxylic acid. The C2H3, right? Those 3 H's, they're part of like the carbon backbone. They're attached to the carbons. But that H that's there at the beginning, that H belongs to the acid portion. So that H is this H over here. That's part of the OH, the carboxylic acid. That's a proton that's released. And you can see an H in the beginning of all of these different acids. Succinic has 2 H's, so that tells me that there are 2 protons for it to lose. But in this case, if I were to give the formula of it being deprotonated, so conjugate base is pretty much just telling me to look for the deprotonated form of the acid, because then that form is now negative, and if it were to react in some way, what it would do is it's going to act as a base, and it's going to go and grab a proton from something, like for example from water. So that's why it's a conjugate base. So in this case, I would write out everything else. So H3O2, the rest of it remains the same, right? Because only the protons are moved, and then the proton is gone from the beginning, and now this thing has a negative charge. So C2H3O2. Oh, well, I was looking at the wrong one, sorry. I was focused too much on acetic acid, but the principle is the same. Now I'm looking at chlorobenzoic acid. So it's C7H4Cl2O, Cl1O2. Essentially just knock out the H, give it a negative charge. That is what I'm looking for. So now C7H4Cl02. C7H4Cl02. That's good. Yeah, that's good. Option D is good. It's not going to be the conjugate base of something, like let's just say it reacts with, I don't know, NaOH. Just as a quick reminder of what conjugate base is, NaCl plus H2O. Conjugate base is just like the matched pair. So like these two things, they're matched. And then these guys are matched. They're matched with each other. So this is a pair. Because on the left side, the chloride, it's in its acid form because it has an H attached to it. So here it's acting as an acid. And then on the product side, it's still a chloride, but now it's going to act as a base because really this is Na plus Cl minus. So since it has a negative charge, it's going to act as a base. All right. So those are the conjugate pairs. The OH from the NaOH, it's a base on the left side, and then on the right side, now it's going to act as an acid. It's OH minus, right? But then it's OH minus plus another H, so it's going to lose one of those H's, act as an acid. So from option A, that OH minus, that's a conjugate. Well, actually, it's the base form of NaOH. It's the conjugate base to like water, but it's not the one for chlorobenzoic acid, and it's not the water either. So remove that answer option. And then the problem with C is that it should be O2, but they removed an O. They kind of treated this as if it were a base, that it lost an OH. But if you draw out the entire molecule, and I'm not going to, but all I really need to draw is the functional group at the end. It's a carboxylic acid. That's the type of acid that we're looking at here. So first of all, like, you should already be like, okay, it doesn't make sense for an acid to lose an O and an H. If it did that, then it would be more like a base, because OH is a minus, it's a negatively charged species. But also, if you were to actually draw out the functional group, you know that's the carboxylic acid, and it makes no sense for that to somehow lose either of these oxygens. Those are like pretty well held oxygens. They're not going to just be lost in the way that a proton would be. So C is incorrect because it took away the oxygen as well. D is the correct answer. Moving on to the next question. So let me just scroll up a bit. Okay. Student E, they accounted for the equivalent weight found for succinic acid by analyzing its titration with NaOH, and then they concluded that it is what? So look at the answer options. It's either diprotic or triprotic. Firstly, what's it asking us? Okay, student E, right? They found the equivalent weight for succinic acid, and then what did they conclude? So first, what is this question asking us? It's saying, go to this table, right? This is the one with the different students. Look at student E. This second last column is showing us that the student found the equivalent weight, meaning they found how much of the NaOH they used up, and then they know the molar mass of the different acids by looking at the table, and they were able to identify that the unknown that they have is succinic acid. So succinic acid looks like this, okay? And then just quickly going back to the answer options, they're telling us that the student concluded that either it was diprotic or triprotic, and it requires either a half or twice, or 3 times the number of moles of NaOH that a normal acid would. So firstly, equivalent weight, what is that talking about? If something has a 1-to-1 equivalent weight, meaning that if I were to have 1 mole of an acid and 1 mole of a base, they would release enough of whatever the acid or basic component is that they would come and combine with each other to neutralize each other. Then if it happens in an equal ratio, that's an equivalent weight of 1. So for example, coming back up here, NaOH plus HCl, if I have these two things, they're going to be in an equivalent weight, meaning if I have 1 mole of NaOH, that's going to be fully neutralized if I have 1 mole of HCl, because the NaOH releases OH minus, the HCl releases the H plus. If I had 1 mole of the HCl, it's going to release 1 mole of the H plus, the protons. But if I have something like H2SO4, for example, H2SO4, that would be diprotic, meaning that it has 2 protons to lose. So if I had 1 mole of this, it can release at a given pKa, or like at a given pH, it's going to release 1 mole of the first proton, but then it has a second proton, or a second mole of protons that it can release. So this one could release 2 moles of protons. So just 1 mole of NaOH wouldn't completely deprotonate this acid. So point is, that's what equivalent weight is. Sometimes you need 2 equivalents of NaOH to completely deprotonate an acid. Sometimes you might need 3 equivalents. What's going on in the case of succinic acid? I want to remove some answer options first by removing the logic. For example, answer option A is saying that if it were to be diprotic, then it requires a half the number of moles of NaOH that you would for a monoprotic acid. That doesn't make any sense. If something was diprotic, that would mean that it releases more than expected protons. It releases double the number of protons, so it makes no sense why it would be half the amount of NaOH needed to completely deprotonate this and neutralize the solution. So it shouldn't be half, it should be the direction should be the other way. It shouldn't be divided by 2, it should be multiplied by 2. Same thing with answer option C. If something were triprotic, it would release 3 equivalents of protons. So you need 3 times as much of NaOH so that you have OH minus to neutralize it. It wouldn't be a third. Just want to remove those answer options first because of the logic. And then when I come over here and I actually start looking at succinic acid, that's the last one in the table. I kind of hinted at this before. For all of the other chemical formulas, this you see like C2H3 up here at the top one, those H's are connected to the carbons. They're part of the carbon backbone. And this H all the way at the end, that is the proton H, the one that's attached to the carboxylic acid, the one that's going to be released. It's separate in the chemical formula because its nature is kind of different, and it makes it clear when you write it this way that it's an acid. For all of them, there's one H at the beginning, but there are 2 for succinic acid. So that means that it has 2 protons to release. Also, look at all of the oxygens for the other ones. You should have been able to realize that those 2 oxygens mean a carboxylic acid. And if there are 4 for succinic acid, that means that there are 2 carboxylic acid groups. If you've done practice with carboxylic acids and their derivatives, and you must have seen acetic acid. So you should be able to, from your knowledge of orgo, determine that this is a carboxylic acid. You should also, I think, be able to draw the compound as well and know that it looks like this, right? I'm seeing 4 carbons. Okay, I draw a 4 carbon chain. 4 oxygens. Okay, that's how I draw them, the carboxylic acids. Those 2 proton H's are there, and then there are 4 hydrogens as well. Yeah, they're over here on the 2 carbons. All of these connections make sense, and I have as many of every element that I should as the formula is showing me. So that is what succinic acid looks like, and now I know it's a diprotic compound. Therefore, I choose option B, and D is incorrect. It's not triprotic. And this is the final question, question 35, kind of just like a logic question. It's saying if a student did not remove all the moisture from KHP before the titration with NaOH, then the molarity determined for NaOH would be what? So if you didn't remove the moisture from KHP, what would the molarity for NaOH be? It would either be too high or too low. That's what the answer options are telling us. So first of all, let's just quickly review what happened over there in this part of the passage. You took NaOH, you were standardizing it by titration with a pure sample of KHP. So since this is a pure sample, you should already know what the concentration of KHP is. But in this case, like if you look at the table, the students got a mass of KHP, and then from their mass, they were able to determine the moles because they have the mass. They have the molar mass as well that was given in the passage, so they know the moles, and then they do a volume of NaOH versus KHP, and that volume allows them to figure out the concentration of NaOH. So when you say mass of KHP, that means that pretty much they were taking it in some kind of solid or powder form, and it had some moisture, but they were supposed to remove the moisture. Whatever the form was, if you know that something was supposed to have moisture removed, and moisture just means water, if there were water molecules in something and you were supposed to take those out before you were doing your experiment, you would know that that now messes with your calculations. In the table, we just showed that they measured the mass of the KHP, and moles is given by mass over molar mass. After getting the mass, they then wrote down, okay, this is my moles. This is how many moles I have of KHP. Since they had water molecules still there because they didn't get rid of all the moisture, their mass is higher than it should be. Therefore, their calculation for moles is higher as well. So now, like, even if it was supposed to be like 1 moles, they're saying that, oh, I have 1.5 moles, but that extra mass was coming from water. So because they're saying that, and then they're doing their titration against NaOH, they're seeing, okay, I need this much NaOH, this much volume of it, so that I can reach the endpoint of this titration. That must mean that this is the actual volume of NaOH I needed. That's what I use for my calculations. But they could have needed like 1 liter or whatever of, or let's say 100 milliliters of the NaOH, but in this case they used 150. They're going to assume that that's the true volume that they needed, and then that is going to give them the true concentration of NaOH. But what actually happened is that they were supposed to only use 100 milliliters, and then at that point they would finish their titration because the KHP and the NaOH would have reacted in whatever way, and you reach the endpoint of the reaction, but they overshot it. They reached the endpoint and then they kept on going because their calculations told them add more milliliters of NaOH, even though now they've already finished the reaction, they've overshot it, and now they're messing everything up by adding more of the NaOH. So hopefully that was clear. Because they now made a mistake, they assumed they had more KHP than they really did, therefore they used more NaOH, and then based on that, more volume, they assumed that the molarity of the NaOH is higher than it actually is. So it's not too low. It's definitely not unaffected. And option D is saying it's unaffected because KHP was dissolved in water. No, you had to first weigh the KHP, and all the moisture should have been removed. When you were weighing the KHP, if the water was still there, it was affecting your calculations for weighing. So the final answer is too high because the actual number of moles of the KHP titrated, the ones that were actually present in the mass that you weighed out, that would be less than the actual number of moles that you wrote down in your calculations. So it's too high, and then that's the correct logic to it. So because of that, A is the correct answer for this final question. Hopefully all of that made sense. I think in this question, the hardest parts were the logic in some of the questions. So if there's anything that was a bit confusing that you don't understand, just make sure to drop a comment down below and we'll get to that as soon as we see it. Otherwise, thank you guys for watching. Hope you found that helpful, and I'll see you guys in the next video.